Dielectric substances that exhibit the piezoelectric effect are known as piezoelectric materials. In nature, most crystals have a piezoelectric effect, but some have a very weak one. Common piezoelectric materials can be divided into two categories: piezocrystals and polycrystalline piezoceramics. Typically, they should possess the following main characteristics: 1. A large piezoelectric constant, 2. High mechanical strength and stiffness, 3. High resistivity and a large dielectric constant, 4. Good temperature and humidity stability, requiring a high Curie point for a broader working temperature range, 5. Piezoelectric properties that do not change over time. In this lesson, we will learn about the piezoelectric materials of piezoelectric sensors, their structure, and practical applications. To begin with, let's learn about the first piezoelectric material, piezocrystals. Piezoelectric single crystals include quartz, both natural and synthetic, and water-soluble piezoelectric crystals, such as potassium sodium tartrate, ethylene diammonium tartrate, and dipotassium tartrate. Quartz crystals are characterized by their extremely stable performance, great mechanical strength, and stable mechanical properties. However, quartz is expensive and has a much lower piezoelectric coefficient compared to piezoceramics, so it is generally only used in standard instruments or sensors with higher requirements. Next is piezoceramics. Piezoceramics are artificially made polycrystalline piezoelectric materials, mainly including barium titanate piezoceramics and lead zirconate titanate piezoceramics. Barium titanate piezoceramics have a high dielectric constant and a larger piezoelectric coefficient. Their drawbacks include inferior temperature stability and mechanical strength compared to quartz crystals. Lead zirconate titanate has a greater piezoelectric coefficient than barium titanate, with electromechanical parameters less affected by temperature, and good time stability, making it the most widely used piezoelectric material in sensors today. In addition, there are also some new piezoelectric materials such as piezoelectric semiconductor materials and polymeric piezoelectric materials. Now, let's learn about the structure of piezoelectric sensors. To enhance the sensitivity of piezoelectric sensors, multiple piezoelectric wafers are often bonded together. The two-piece structure is the most commonly used. Since the charges on the piezoelectric elements are polarized, there are two connection methods, series and parallel, with the parallel connection being typical. Connecting piezoelectric wafers in parallel can increase output charge and enhance sensitivity. When used, a certain preload must be applied to both wafers to ensure that the piezoelectric elements are always under pressure during operation, which also eliminates nonlinear errors caused by poor contact between the two wafers, ensuring a linear relationship between output and input force. However, this preload should not be too high, as it would affect their sensitivity. Finally, let's look at the applications of piezoelectric sensors. Piezoelectric sensors have a wide measurement range, capable of measuring dynamic and static forces from a few hundred to tens of thousands of newtons. Moreover, they offer advantages such as simple structure, small size, light weight, high natural frequency, and high resolution. Let's discuss a few common applications with examples. First is the glass break alarm. When glass breaks, it emits vibrations in thousands of hertz. By adhering polymeric piezoelectric film to the glass, a glass break alarm can detect these vibrations. On both sides of the polymeric piezoelectric sensor, transparent tin dioxide conductive electrodes are sprayed. During use, it is glued to the glass with an adhesive. When the glass is violently shattered, the piezoelectric film senses the intense vibration and generates a narrow pulse signal between two output pins. This signal, after amplification, is transmitted via cable to a central alarm device, triggering an alarm signal. The second application is vibration test with piezoelectric sensors. Piezoelectric accelerometers are widely used in vibration measurement systems due to their small size, light weight, and broad measurement range. A typical vibration measurement system consists of a piezoelectric accelerometer, charge amplifier, and dynamic signal analyzer. The vibration acceleration signal from the measured object is transmitted by the sensor and then sent to the system's charge amplifier via the sensor cable. The charge amplifier converts the signal into a voltage signal and amplifies it. After sampling by a data acquisition tester, the collected signal can be displayed and processed in real time on a monitor. This can be used for testing vibration rollers at construction sites. The third application is piezoelectric alarm systems. Piezoelectric alarm systems can be used for entrances and exits of important locations, as well as perimeter security protection. By burying long piezoelectric cables in the shallow layer of soil, they act as distributed underground microphones, capable of detecting human footsteps or wheeled and tracked vehicles within a range of tens of meters. In this lesson, we learned about the meaning of the piezoelectric effect and the piezoelectric effects in two common materials. You can review some materials after class to learn about the applications of new piezoelectric materials in piezoelectric sensors and discuss them with your peers. That concludes our lesson for today. Thank you all.